Hey, Algebra 2 honor students, today is going to be Unit 12, Day 5. Today we're going to be talking about solving log equations, which we've had a little bit of experience with already and talking about log properties. And we're going to see how log properties plays a pretty large role in terms of being able to solve log equations successfully. So in order to get started today in your notes, let's write down some lovely steps. There's my drawing of some steps. In order to solve some log equations, step one being you have to condense all of the logs on each side. So if you have multiple logs on both sides of the equation, you want to condense them so that you have a single log on both sides. There are times where you only have logs on one side of the equation anyway, but if there's multiple logs, you do need to condense them into a single logarithm. Okay, step two is a pretty important one. Convert to exponential form, and I wrote if necessary. There's going to be cases today where we don't need exponential form, and I'll explain why. But if you have logs really just on one side of the equation, once you've condensed them, you then want to convert to exponential form. It's not necessary if you have logs on both sides of the equation. And then finally, once you've converted to exponential or you've set some quantities equal, you're then going to solve and check. And you can see that that check part I'm pretty excited about, and I've underlined it a couple times because there's definitely times where we get solutions that don't check out. Specifically, if you plug back in and you're taking the log of 0 or the log of a negative number, those are both not great situations. They are not in the domain of a log function. Think back to the day that we did domain, okay? So if you get an answer such that when it plugs into the original, you get either 0 or a negative number, we're going to reject that solution, okay? All right, so if we're okay with those steps, let's go right into the practice then. The first example we're going to take a look at is log x plus log 14 equals log of 98. Okay. So just like I stated in step number one, if you have multiple logs, which we do on the left side, we want to start by condensing those logs. All right. So in thinking about that left side right there, when I see addition, I know that addition condenses to multiplication. So this is going to turn into log of x times 14, which I think is just nicer if we write it as 14x. And that equals the log of 98. Now remember, there's no base written in here. We're dealing with log base 10. But the fact that we're dealing with log base 10 technically actually doesn't matter in terms of what I'm going to do next. Because if you have log base 10 of this quantity equals log base 10 of that quantity, don't these two quantities have to be equal? It's sort of like when you solve an exponential equation when you have common bases. If the bases of an exponential are the same, you set those exponents equal. Well, very similarly, these quantities inside the log, those have to be equal in order for the statement to be true. So you can kind of drop the logs at this point and then say that 14x equals 98. And if you divide by 14, you very quickly here get that x equals 7. And sometimes log equations can be solved that quickly. I think we've done one similar to this in one of our recaps, but if not, here's our first time kind of seeing that if we condense first, then we can set those inside parts equal. Okay, let's do kind of a slightly different style equation. So for number 2, log base 2 of x plus 5 minus log base 2 of x minus 2 is equal to 3. Now, the reason why I say this one's a different style is not because it's actually subtraction, even though that will make a difference. It's because I don't have logs on the right side of the equation. This one just equals the constant of 3. Okay, so regardless of that, we're actually still going to start by condensing the logs on the left side. So when you condense subtraction, that becomes division. So it's going to be log base 2 of x plus 5 divided by x minus 2 is equal to 3. And then once you condense the logs, we now have to go back to what step 2 said not too long ago. Okay. Step 2 says convert to exponential form if necessary. It's necessary if there's no log on this side. So remember that in exponential form, it would be the base to this exponent equals what's inside the parentheses on this side. So therefore, x plus 5 over x minus 2 is equal to 2 to the third power. And once you convert to exponential form, it's typically a pretty easy equation to solve. X plus 5 over x minus 2 is equal to 2 cubed, which is 8. At this point, you either multiply both sides by x minus 2 or put that set over 1 and think about cross multiplying. So you get 8x minus 16 when you distribute equals 1 times x plus 5, which of course is just x plus 5. Subtract x over here to get a 7x. Add the 16 to this side to get 21. And therefore we get x equals 3. Now, I haven't really talked about that check part of the process, but it is important to look back up and say, if I plug in 3 to the original, is it going to be okay? Like 3 plus 5, as long as it's a positive number, typically you're in the clear. So 3 plus 5, that's okay. 3 minus 2 is also a positive number. So I think we're kind of good to go as far as that's concerned. If you want to see if this is the correct positive number, well, then plug it in and evaluate, right? If I do 3 plus 5, that would be log base 2 of 8. If I do 3 minus 2, that's going to be minus log base 2 of 1. And log base 2 of 8 is 3, right? Because 2 to the third is 8. Minus log base 2 of 1, well, 2 to what power is 1? 2 to the 0 power is 1. Remember, log base anything of 1 is always 0. So therefore, that equals 3, which is what's on the other side. So you can even go that step further and physically check, is this the right answer? But typically, all I'm checking for is that when I plug this back in, I'm not taking the log of something negative, because that's really bad news. That we can cross off immediately. Okay. All right, let's try a couple of other situations. So for the next one, let's also bring in some natural logs into our equation. Natural logs are pretty fantastic, right? The same thing as log base e. So we got ln x plus the ln of x minus 2 is equal to the ln of 48. Okay, so to start this one, if we have multiple logs, we know we have to condense first, and I see addition, which is going to condense to multiplication. So we got ln of x times x minus 2 is what's on the inside there. And then that equals the ln of 48. This is similar to the first question that we started with today, in that now that we have a single natural log on the left and a single natural log on the right, these inside quantities can be set equal. Okay, so I don't need that exponential form. If ln of this equals ln of that, this and that have to be equal. So go ahead and set those quantities equal. And from here, just be careful. It kind of looks like, oh yeah, we've already factored something, but you can't solve anything unless this is set equal to 0. So I am going to distribute that x to make it x squared minus 2x. Subtract the 48 over while we're at it and set it to 0. So we get a quadratic that we can factor. This factors into x minus 8 and x plus 6. So in the end, we get our two solutions of x equals 8 and x equals negative 6. Okay, x equals 8 is totally fine. X equals negative 6, though, come back to the original. The ln of negative 6 is going to be really bad news. Okay, can't take the natural log of a negative. So therefore, x equals 8 is the only solution we would accept here. Are negative solutions always going to get crossed off? The answer is no. Sometimes negatives work, and it is rare that they do work, but for example, if this said x plus 7, it would have been okay, because negative 6 plus 7 is still a positive number. So you want to make sure that you're checking, because to that reason, by the way, sometimes positives don't work. This positive 8 does work. 8 minus 2 is a positive number. 8 is certainly fine in that spot as well. But you want to make sure that don't rely on like, oh yeah, negatives never work and positives always work. That's actually not the case, okay? Plug them back into the original equation. Make sure you're not taking the natural log or the log of anything that is a negative or 0. Okay, let's just do one more for today. So the last equation we'll solve is the ln of x plus 2 plus the ln of x equals 0. Okay. So we're definitely going to start by condensing, and it looks kind of similar to the last one in that when I condense, you're going to get x times x plus 2 instead of x times x minus 2. But the key difference here is we don't have a natural log on this side. So this is where we're going to go to that step where once you've condensed the logs, you're now going to convert this to exponential form. When I do that, we have to remember what's the base of the log that I'm working with when I write ln, the natural log here. We never write that in, but it's really log base e. And if it helps you to think of that base e as being down there, we know that x times x plus 2 would equal e to the 0 power, right? the base to this exponent equals this number on the inside. So that's what the exponential form looks like. So like we did in the last one, distribute that x in to get x squared plus 2x. And I feel like we're a little nervous, like, uh-oh, we have e in our equation, but we kind of don't, do we? E to the 0 is just 1. And if we had e in the equation, actually still would have been okay, but it makes it a little bit more comfortable for us when we see that that's just the number 1. So I'm going to subtract that over, set it to 0, and I'm going to caution you here because this is so close to being something we can factor. If it was a +1, we'd be in business, but with the -1, there's no pair of factors that multiply to give you this trinomial. Okay, so if I can't factor it, does that mean I stop and say no solution? No, not even in the slightest. We either have quadratic formula or complete the square. Those are your options. And the option that I'm going to go with, just because b is even, x squared's coefficient is a 1, I think complete the square, just in my opinion, is easier. I think I converted some of you back when we were doing a lot of complete the square. If you like quadratic formula, you'll still get the same result. So completing the square actually has you move the constant back over to the other side. Add this 1 over. And then you take the middle term, divide it by 2, and square it. So 2 divided by 2 is 1. Squared is this 1 right here. So you've got to add 1 to both sides. This becomes x plus 1 squared. That's a 2. Square root. X plus 1 equals plus or minus. Don't forget about that plus or minus the square root of 2. And finally, subtracting the 1 over gives you -1 plus or minus radical 2. Okay, the question is, do they both check, right? We have -1 plus and -1 minus radical 2. And it turns out the only one that checks out is -1 plus radical 2. Radical 2 is about 1.4. So -1 plus 1.4 is a positive number. And it's going to work when I plug it in for x in the original. -1 minus radical 2, however, is not going to work out well because that's a negative number altogether, and ln of a negative is non-existent. So you do have to be a little bit cautious that even when I do the quadratic formula, or complete the square, that plus or minus, when you separate it, we know it represents 2 solutions. Only one of those checks out. So probably a little bit tougher conceptually on that one, but hopefully that makes sense. We will do some more solving practice next time we are in class. If you have any questions, let me know, but have a great rest of your day.